Alrighty, so we're going to begin thermodynamics by talking about temperature, of course, and a topic called calorimetry. So, temperature, we're all fairly familiar with the concept of temperature. We use it a lot in our daily lives. It's actually, in terms of physics, a fairly difficult thing to actually define. How does one measure temperature? Of course, we can measure the temperature of a liquid by sticking a thermometer in it, for instance. Or, if you're frying up some French fries, you have a little thermometer you could stick in the oil to see what the temperature is. However, how do you measure the temperature in let's say, in space? Is it cold or is it hot? We usually think of space as being very cold, but actually, if you think about temperature more physically, temperature deals with the motion of atoms. The faster atoms are moving around, the hotter the object is. Then the temperature in outer space should be very hot because the particles that are passing through space are moving at very, very high speeds. But we think of it as cold because there's very few particles. So if you were to try to feel what it felt like, it would feel cold, even though, in terms of how fast the particles are moving, it should be hot. So temperature is kind of a awkward thing to try to measure, but we have a good conceptual outlook on what temperature is, which is sufficient for what we want to do. First thing we need to realize about temperature is, just as in everything in physics, there are certain units we need to worry about when we measure the temperature. For instance, saying it's 60 degrees outside, well, is that good or is that bad? Or let's say 30 degrees. If someone said it's 30 degrees outside, would you think that's cold or would you think it's hot? Well, of course, it depends on what units we're talking about. If you're here in America and we're using Fahrenheit, then obviously 30 degrees is fairly cold. It's below freezing. But if you're in England and they're talking about Celsius, then all of a sudden 30 degrees Celsius is a hot summer day. So we need to know about the units we're talking about when we discuss temperature. And I just gave you the two main ones that we use most often in our everyday lives. There's Fahrenheit and there's Celsius. Now, one thing we may want to do is convert between them. Say I tell you it is 25 degrees Celsius. Maybe the temperature of the room is 25 degrees Celsius. But you don't really know what Celsius is. You don't really have a good feeling for it. So you want to know, what is that in terms of Fahrenheit? The conversion says Fahrenheit temperature. You take the Celsius temperature, multiply it by 9 over 5, and add 32 to it. That's how you convert from Celsius into Fahrenheit. So you take the Celsius temperature, multiply by 9 over 5, whatever that number is, add 32, and you have Fahrenheit. And obviously you could go the other way. Let's say you wanted to know the Celsius temperature. How would you do it? Well, just take this first conversion and solve for C. So you would have the Fahrenheit temperature minus 32, and then that whole thing you multiply by 5 over 9. So these are conversion factors. If you ever need it, then this is how you would do it. Take the temperature, do this little calculation, and you have the new temperature. And of course, we know for Fahrenheit, water freezes at a temperature of 32 degrees for Fahrenheit, and water boils at 212 degrees. For Celsius, water freezes at 0 degrees, and it boils at 100. And in fact, Celsius temperature scale was defined by choosing these numbers. They said, water we're going to think of as important. We didn't have to. We could have said, what's the freezing point of alcohol or some other thing. But because we're humans and humans rely on water, water is extremely important to us. We said, let us take water as the standard. What's its freezing point? When does it freeze? Whatever that temperature is, we're going to call that 0 degrees. And then when does it boil? Whatever that temperature is, we're going to call that 100. And then we're going to create the scale to fit that. That's how centigrade or Celsius was created. Now here's the issue. As I said, water is not some magical thing in the universe. It's just one of millions or billions of molecules. So in terms of physics, in terms of fundamental nature of the universe, there's nothing special about water. And in fact, 0 degrees is not as cold as it can get. Things can get colder than 0 degrees. And so for physics, we needed a scale, a unit scale, where we define 0 to be as cold as possible, because why in the world do you want negative temperatures? You don't have to have it. So make the very coldest temperature in the universe, make that 0 degrees, and everything else is higher than that. And so the Kelvin temperature scale was created. And the good news about Kelvin is that the size of the degrees, the size of the unit of Kelvin, happens to be the same as the size of a Celsius. This isn't true about Fahrenheit and Celsius. Obviously, if Fahrenheit could go from 32 up to 212 for the freezing and boiling point, but Celsius from 0 to 100, there's a lot more degrees in Fahrenheit between freezing and boiling. Not as many in Celsius. So that means how big a unit of Celsius is relative to Fahrenheit is bigger. If you change by 1 degree Celsius, you're changing by multiple degrees Fahrenheit. They're not the same size. But for Kelvin, they defined Kelvin, when they created it, to be the same size unit as a Celsius. It just starts at a different place. And in fact, Kelvin starts at what's called absolute 0. Absolute 0 is, exactly as the name implies, the coldest temperature we can get in the universe. Whatever that temperature is, we call it 0 Kelvin. So what is that temperature? Well, it happens to be negative 273.15 degrees Celsius. So if we measure the coldest temperature we could possibly get in Celsius, it's negative 273 degrees. So that temperature is defined as 0 Kelvin. So what does that imply? That implies that if we want to know at what temperature in terms of Kelvin does water freeze, well, of course, it freezes at 273. Because what you can say is that the Kelvin temperature is going to be whatever the Celsius temperature is, but then you add 273 degrees to it. So that's an easy conversion. Take the Celsius, let's say 0 degrees Celsius, add 273 degrees, and now you have the temperature in Kelvin. And that's purely because the size of the units are the same size. See over here with this 9/5 stuff? That's because the size of Fahrenheit and the size of Celsius are not the same. So you have that multiplying factor you have to worry about. But for Kelvin, everything's fine. You just add 273 to Celsius and you got your answer. So, as we see, the freezing point of water in terms of Kelvin, 273. What about boiling? Well, you take the Celsius and add 273. So it's 100 plus 273 is 373. For now, I'm just getting rid of the 0.15 thing. We're not going to worry about that. We're just going to say 273. Also, make a little note of this. When I write the Kelvin temperature, I don't call it degrees Kelvin. Now, I don't know why they chose this, but the units of Kelvin are Kelvin, not degrees Kelvin. In Celsius, it's degrees Celsius. So how hot is it? It's 38 degrees Celsius. If you say Kelvin, how hot is it in Kelvin? It's, 47 Kelvin. You don't say degrees. So that's just a little note to make. It's not important, but if you want to be correct about saying things, just note there's no such thing as a degree Kelvin. It's just plain Kelvin. Now, why did I go through this? Because, as I said, in terms of physics, Kelvin is the temperature scale we use. So that means any equation that requires the use of temperature, we have to use temperature in Kelvin. Just like in last semester, all of our equations relied on distances in meters or time in seconds. Well, now we need temperature in Kelvin. Now, I say this, but I'm going to give you a little hint. And you have to be careful with this hint. In truth, yes, all the equations have to be in Kelvin. However, because Kelvin and Celsius are the same size units, if you ever have an equation that wants a change in temperature or the difference in temperature, so for instance, delta T or T2 minus T1, things like this, well, think about it. If I have a change in temperature, final minus initial, T2 minus T1, if I write it in Kelvin, then it's going to be something like this. Remember, the conversion for Kelvin is Celsius plus 273. So Kelvin 2 is the Celsius 2 degrees plus 273 minus Kelvin 1, which is Celsius 1 plus 273. Right? So this is the temperature 2 in terms of Kelvin, temperature 1 in terms of Kelvin, but I wrote it as Celsius degrees, the conversion factor. Well, notice what happens. This thing becomes C2 plus 273 minus C1 minus 273. Notice this minus is because you distribute the minus. And so with that, notice this 273 cancels that 273, and you're left with C2 minus C1. So what does this tell me? This tells me all equations need Kelvin temperatures. However, if the equation doesn't just have temperature, but has change in temperature, or the difference between two temperatures, then you can also write it in terms of Celsius. Because a difference in Kelvin is the same as a difference in Celsius. Okay? So that's a little shortcut. Later on, when we have our equations and we're working out problems, if you don't want to have to convert, you don't have to if the equation is asking you for a change in temperature. If, however, the the equation is something like sigma epsilon t to the fourth, well, notice this doesn't ask for the change in temperature. This is asking you what is the temperature to the fourth power. This has to be in Kelvin. But if I have Cm delta T, that's asking for the difference in temperature. This can be Kelvin or Celsius. Okay? So that's nice. On a test or something, if the equation wants the difference, then you could save time by not having to convert. But be careful, because you have to understand when you do have to convert and when you don't have to. If you're afraid you're going to make a mistake, and you don't want to make a mistake, then always convert. You'll never be wrong if you convert. However, if you're sure of yourself or you've practiced and you see and you understand the rule, then convert when you have to and don't convert when you don't have to. And you'll be fine. All right, so that's temperature. Now, what's the first real system we're going to deal with where we can actually calculate stuff? We can predict. We can actually use physics. This is going to be called calorimetry. Calorimetry is pretty fun because it's kind of like, the problems at issue are kind of like detective problems. You're given a system with a whole bunch of information, and you're asked to predict something or to figure something out from that information. Generally, it has to do with you put a whole bunch of things together, everything's at different temperatures, you add them all up, you mix them all up, and this new thing will now be at some new temperature. What will that temperature be? Or you have a cup of hot coffee and you put a certain amount of cold milk in it. What will the temperature of the new mixture be? You're going to cool off the coffee, obviously, but how cold will it get? Or if I want to cool off my coffee and I want it to get to an exact temperature that's perfect for me to go ahead and drink without burning my tongue, how much of ice should I put in it? Or how much cold milk should I put in to get it to that perfect temperature? These are the types of problems that calorimetry deals with. So what do we need to know to deal with calorimetry? Well, first of all, at its heart, a calorimetry problem is really conservation of energy. Well, we remember from first semester physics, conservation of energy basically says whatever energy is in the system, it's the same energy the whole time. It never changes. Now, you can convert from one type of energy to another. So, for instance, you hold a marker or a piece of chalk or something up in the air, a certain distance above the ground. The system has a certain amount of energy. It's called gravitational potential energy. Because it's a distance above the ground, there's some potential energy stored within that system. And then you let go of the chalk. Well, what's going to happen? Of course, we know the chalk's going to fall. But what does that mean? Well, what's happening is the chalk is getting faster and faster as it falls. That means it's gaining more and more kinetic energy. But we just said conservation of energy says you can't gain energy or lose energy. You have the same energy the whole time. Well, the reason you're gaining kinetic energy is because as the chalk falls, it's getting lower and lower closer to the ground, so it's not as high. If it's not as high, it's got less gravitational potential energy. And so really what's going on in your system is you're taking potential energy and you're converting it into kinetic energy. But if I analyze the system and I add up the total energy, it's going to be the same total energy as the beginning of the problem was. The same thing's going to happen here. Only for the energy I'm going to talk about now, we're talking about heat energy. So instead of a certain amount of energy because you're a distance above a ground, or you're compressing a spring, or there's kinetic energy because you're moving, this is heat energy. Because of its temperature, because really the vibration of the particles and things like this object, this system that's at a certain temperature will have a certain energy. The hotter it is, the higher its energy, the more heat there is. So, if I take two objects, so take object 1 and object 2, that are at different temperatures, this guy is at T1, let's say, this guy's at T2, and I combine them together into one big object, I'd like to know what will the temperature of this new object be. How will I be able to figure it out? Well, if I know how much energy this guy had and how much energy this guy has, when I combine them, this guy's going to have the total energy of the two things put together. So all I'll have to do is figure out if it's got that total energy, well, what temperature is that energy? But even easier than that, I don't even have to do that so much. That would work. Even easier, you could think of it this way. Say object 1 is very hot. Object 2 is cold. When I put them together, what's going to happen? Well, this is intuitive. Object 1, the hot guy, is going to get colder because object 2 is going to cool it off. And vice versa, object 2 is going to warm up because object 1 is heating it up. So that means, if we think of it like this guy has a much bigger energy than that guy. Energy 1 is bigger than energy 2. So when you put these two objects together, object 1 is going to give a lot of energy to object 2. If object 1 gives energy to object 2, object 1 now has less energy, so he gets cooler. Object 2 now has more energy, so he gets hotter. And they keep moving energy back and forth between themselves until they're at the same energy level or they're at the same temperature. If they're at the same temperature, then there's no reason object 1 is going to give energy to object 2, because object 2 can't accept anymore. He's just as hot as object 1. This is the conceptual view of what we're going to do. We're going to say, if you have multiple objects in your system, they all have different heat energies. If we put them together, whatever heat is lost by one object must be gained by the other object, such that the total energy of the system does not change. So if we say that, we have to know, first of all, the variable for heat energy is called Q. Heat energy is Q. I don't know why they decided to use that variable, but that's what they use. And so what we're going to do is have a system, and we're going to say, if we add the heat energy from one object, add it to another, however many objects are in our system, the total loss or gain, the change of this energy is equal to 0. Which makes sense. Like I said, let's say object 1 is a lot hotter than object 2. That means object 1 is going to lose a bunch of energy. So he's going to have like a negative energy. But however much he lost, object 2 gained it. So he's going to have a positive energy. And they cancel each other out. Whatever one gains, the other loses, and vice versa. You don't have all of a sudden this mysterious energy out of nowhere that changes the system. They all had their energy. I put them together. They still have their energy. But some of one may have gone to another, and they may have moved around. You've converted one energy to another, but the total energy is constant. So if you have that concept in your mind, then calorimetry is going to be very easy. The hard part of it is knowing how much heat energy does an object have, obviously. If I give you a cup of coffee and I say how much heat energy is there, how the heck do you know? But if we wanted to calculate it, how would we do it? Here's the equation. The amount of heat energy in an object is equal to a variable called C, which I'll talk about, times how much of that object do you have, that's the mass, times the amount of temperature loss or change in temperature of that object. So for instance, if I have this cup of coffee and the coffee is going to go from 100 degrees down to 80 degrees, there's a certain amount of heat energy that was lost by that coffee. How much heat energy is lost? This much. The more temperature you change, the more heat energy you're losing or gaining. Now, let's talk about these variables. So this is delta T, that's change in temperature. This is mass. How much of that object do you have? Of course, if you have a really large cup of coffee and you cool off, then you've lost a heck of a lot of energy. If you have a little bitty thimble of coffee and you cool off, then only a little bit of energy was lost. Now, what's the C? The C is called the specific heat. And this basically tells you, or this is a characteristic which defines the object we're talking about. Because it would make sense that coffee may be able to store more energy than, I don't know, a piece of wood, or than cotton, or a metal bar, or a glass window. All these different objects take certain amount of energy to change their temperature. And that's what specific heat is. Specific heat tells you how much energy is required to change 1 kilogram of the object by 1 Kelvin. So if I want to change the temperature of an object, the specific heat tells me how easy is that to do. If it's really easy to do, then the specific heat is going to be very small. It doesn't take that much heat to change the temperature. If the specific heat is very large, that means I have to stick a heck of a lot of energy into it just to change the temperature by 1 degree. Now, how do I know what the specific heat is? You don't know. This is something people do experiments and they write it down in tables. You're not going to have to memorize the specific heat of all these different objects. We're going to use one a lot, and so you should know that. The specific heat of water is 4186. Okay? So that's just a number. We're going to use it a lot. You may as well try to remember it, but any specific heat you need on a test or in a homework problem, those specific heats will be given to you. If you don't know them, you could Google them. You just say specific heat of water or specific heat of brass or whatever the object is. The units for all of this stuff we should take a look at. First of all, Q, heat energy, the units are joules, of course. Same unit as energy. What are the units of everything else? Well, let's look at mass. Mass is kilograms. Change in temperature, that's Kelvin. So what about specific heat? It's the amount of energy required to change 1 kilogram by 1 Kelvin. So it's joules per kilogram Kelvin. So when you're looking up on Google, for instance, you may see different numbers for the specific heat. You may see 1,000. You may see 4.186. It's all about what units they're using. Our units are joules per kilogram Kelvin. You may also see joules per kilogram Celsius. Because again, since we're using change in temperature, we're allowed to use Celsius instead of Kelvin. You might see, which a lot of times in chemistry you'll see, calories per gram Celsius. Calories is a different unit for energy. We're not going to use calories in this class. We're using joules because we're physicists. We're not chemists. But just note that in other units, this number 4186 will be different. Like I said, I believe if you use calories, it's probably 1,000, if I remember correctly. All right. So now we know how much energy is lost or gained by an object because of a change in its temperature. And again, specific heat, that's something that's given in the problem or you look it up or whatever. It's not something you need to know just off the top of your head. Now, how do I use it to do a problem in calorimetry? What you're going to do is this. We're going to say, okay, let's say we have three things in my system, Q1 plus Q2 plus Q3. So I've got three things in my system. I've put them together, and now I want to know what will the final temperature of the system be. Everything equalizes, it's all stirred up into a big solution, and I want to know what the new temperature will be. Well, all we have to do is for each one of these Q's, plug in a Cm delta T. So this becomes Cm delta T for object 1 plus Cm delta T for object 2, and then Cm delta T for object 3. And equal to 0 because whatever Cm delta T is lost by 1, it's gained by 2. So when you add up all the losses and gains, you get 0. Once we have this, then all we have to do is start plugging numbers in, which we'll have in our problems. So we'll have some C1, some M1. Delta T becomes TF1 minus TI1 plus C2, M2, TF2 minus TI2. And the same for 3. Equals 0. And then note that if we put all this stuff into the same system and everything equalizes, then TF1, TF2, and TF3 are all the same temperature. Everything gets to the same final temperature. So instead of calling it TF1, I just call it TF. This is just TF, the final temperature of the system. Everything else I'll know. They'll all be numbers. And so now I'll just have one equation with a whole bunch of numbers and TF as the unknown variable. And so I just solve it for TF. That's basically what we're going to do for these problems. Now, of course, I don't have to ask for the final temperature of a system. I could ask one of the other questions which I mentioned earlier. Let's say I have a cup of coffee that's at 100 degrees and 100 degrees Celsius. And I want to know how much milk should I put in the coffee if the milk is at 5 degrees, such that the cup of coffee gets down to 85 degrees. For that type of problem, I already know what the final temperature is. It's 85. So what is it I'm looking for? I'm looking for how much milk to put in. That means I'm looking for the mass of the milk, M2. So in that problem, I'd have all the numbers, but M2 would be my unknown. But again, it's still just a normal algebra equation. Whole bunch of numbers, one little unknown sitting there, solve for the unknown. No matter how I ask a question in calorimetry, it must be that you have every single variable, every single piece of equation, except one single variable. And that's the thing you're going to be looking for. So nothing fancy, no two equations, two unknowns, or anything like that. It's a matter of, can I look at the system and see each part of the system individually, plug in all the numbers for each part in the correct way. Once I've done that, just find the variable, and that's it. So, with that, let me do one example so you could get a better firm grip on what we're doing. Here's the question. You place, let's say, 10 grams of milk at 5 degrees Celsius into a 100-gram cup of coffee at 100 degrees Celsius. If the specific heat of milk is, let's say, 3,000, and the specific heat of coffee is 4,000, just to give numbers, what will the final temperature of the system be once it reaches equilibrium, of course? That is, you put the milk in and you don't test it right away. You let it sit for a little bit, you mix it around so it all settles, and then you test the temperature. All right, so how do I do this? Well, what you have to do, and this is how I go about every single calorimetry problem. Some can seem more complicated because there's a bunch of pieces. Some are less complicated because maybe there's only two pieces. Here, there's only two pieces in my system. What are they? I've got how much energy is gained or lost by the milk, and I've got how much energy is gained or lost by the coffee. And all I want to do is take Qm plus Qc equal to 0. Because the milk, which is at 5 degrees, is being placed into the coffee, which is at 100. What's going to happen? The milk is going to heat up because of the hot coffee, and the coffee is going to cool down because of the milk. So coffee loses energy, milk gains that energy. And they cancel out and you get 0 because you don't lose as a whole. Whatever was lost was gained by the other. So this is the equation I want to solve. How do I solve it? Well, I need to know, what are these Q's? Well, Q for milk is C for milk, M for milk, and delta T for milk. And C for coffee. C for coffee, M for coffee, delta T for coffee. And now I take these things and I plug it into my equation. So here we go. Q for milk becomes C for milk, mass of the milk. Delta T for milk means the final temperature minus the initial temperature of the milk. Notice I don't have to say final temperature of milk. The final temperature of the milk is the same as the final temperature for the whole thing. So I'm just calling it final temperature. And then for coffee, I have C for coffee, M for coffee. And then I have final temperature minus the initial temperature of the coffee. There's my equation. Plug my numbers in. What's the specific heat of milk? There it is, 3,000. How much milk do I have? The mass of the milk, 10 grams. Bad units. Grams is not a good unit. So I need to convert grams to kilograms. So how many grams are in a kilogram? 1,000. If I have 10 grams, how many kilograms is that? Well, it's 0.01 kilograms. Okay? You take the grams and you divide by 1,000. So 0.01 is the mass of the milk in terms of kilograms. Remember, you need to write units. And now I need final minus initial temperature. Generally speaking, I would make this Kelvin. However, if you remember my little shortcut trick, because I'm taking the difference between two temperatures, I can use Celsius. So I don't have to convert this temperature. So what's the final temperature? I don't know. That's my unknown. What's the initial temperature of the milk? 5 degrees Celsius, so 5. All right, now the coffee piece. Specific heat of coffee was told to be 4,000. How much coffee did I have? 100 grams. So how many kilograms is that? That's 0.1. Final temperature, I don't know, but that's my unknown. Minus initial temperature of the coffee, 100 equals 0. And now you can see my equation. All a bunch of numbers. The only unknown here is TF. What do I do now? Well, now I try to simplify it. I calculate everything through. So I have 3,000 times 0.01 times TF. So 3,000 times 0.01 is 30 times TF. And then I have 3,000 times 0.01 times negative 5. And that's negative 150. Remember this negative. Don't forget the negative there. Then I have plus 4,000 times 0.1 times TF. That's 400 times TF. Then I have minus 4,000 times 0.1 times negative 100. So that's 40,000. Equals 0. So all I did was I distributed things through. 3,000 times 0.01, multiply those things, you get 30. So that 30 is multiplying the TF and the negative 5. So I have 30 TF minus 150. And then over here, 4,000 times 0.1, that is 400. So that 400 is multiplying the TF and it's multiplying the negative 100. Okay. So now, unfortunately, let me erase this just to give myself a little room. And now I'll go here. Forgive me for running out of room on this sheet, but I don't want to go to the next page. I want you to see the rest of the work. So I'm taking this. I have 30 TF. I'll rewrite it. Minus 150 plus 400 TF minus 40,000 equals 0. Collect the TFs and everything else goes to the other side. 30 TF plus 400 TF is 430 TF. On the other side, I have 40,000 plus 150 is 40150. Remember, it went to the other side, so it became positive. They both became positive. All right, this is easy. Just TF is 40150 divided by 430. And I'll stick that in my calculator, 40150 divided by 430. And what do I get? I get 93.4 degrees Celsius. Now, of course, before I box it, I should ask myself this question. The question is, does this answer make sense? Can I see, just by looking at it, whether it's right or wrong? And in this case, I can. I can't see if it's definitely right, but I can see if it's definitely wrong. Think about what the question is saying. I have this really hot cup of coffee that's at 100 degrees. I put a little bit of cold milk in it. What's the new temperature? Well, intuitively, use your intuition here. What do you think the temperature is going to be? Is it going to be bigger than 100 or is it going to be less than 100? Obviously, it should be less than 100. You're cooling it off by putting some cold milk. Now, is it going to be way less than 100 or just a little bit less than 100? Well, let's see. Do I have a lot more coffee or a lot more milk? If I have a lot more milk, then the milk is really going to cool off the coffee. If I have a lot of coffee and only a little bit of milk, then there's not enough milk to really make that big of a difference. Well, here I have 100 grams of coffee, but only 10 grams of milk. I've got way more coffee than milk, so it should only be a little bit less than 100. Now I look at my answer. What did I get? 93. That's less than 100, but not way, way less. It's not like 2 degrees or something. And so, seems very legitimate to me. It could still be wrong. Maybe I did a little calculation mistake somewhere. But at least, looking at it, I can't tell if it's definitely wrong. If I would have gotten an answer that said maybe 120, well, I know that must be wrong. I wouldn't accept it. I'd go back and see where I made a mistake. Because I know if my coffee started at 100, it didn't heat up by putting cold milk in it. It cooled off. Also, another thing I know, if I got 3 degrees as the final answer, that can't be right either. How do I know? Well, the coldest it could possibly get is how cold the milk was. And the milk was at 5. So you can't possibly put 5-degree milk in some coffee and get colder than 5 degrees. It had to get warmer than 5. So you know for sure it has to be between 5 and 100. So if you get something outside of that range, you know for sure you did something wrong and you go back. Here, thankfully, we got something in the range, so I'm going to accept it. I don't see anything I did wrong here necessarily. Maybe I did and you'd catch it, but if this is me on a test, that's how I do a check. I look at the answer, I say, does it make sense? Could this possibly be the right answer? To me, this could be the right answer, so I'm going to go ahead and accept it and move on to the next question. But that's how we do this type of problem, calorimetry. We're given a system with multiple pieces in the system. Each piece has its own little temperature. We put them all together and let the system come to equilibrium. That means they all come to the same final temperature. And then in this case, the question was asking, what is that final temperature going to be? How do I solve a problem like this? I start by saying, what is every single piece in my system? For this problem, there were 2 pieces. There's the milk and there's the coffee. So I'm going to have 2 Q's. Q for milk, Q for coffee. I add those 2 things and I equal to 0. From there, I say, okay, what are my Q's? Q is Cm delta T. So I have Cm delta T for milk and I have Cm delta T for coffee. All of those variables I have numbers for in this problem, except final temperature. So I plug the numbers in, and I get my little equation. Sorry, some of this stuff is, for some reason, erasing. Maybe I moved my hand over it. Oops. I'll plug my numbers in, TF is the only unknown, and then I go through the process of solving it by algebra. In this case, distribute the numbers through, make sure you're multiplying every number correctly, you're keeping track of your negative signs. Multiply them through, you get this final equation that looks like this. Collect the TFs on one side, numbers on the other side, solve for TF, and you get your final temperature. Once you get that temperature, you ask if it makes sense. You look at it. Is it in a range of possible answers? It is. So you accept it and you box your answer. All right. So I hope this is a good introduction to calorimetry for you. Unfortunately, calorimetry problems do get slightly more complicated. First of all, of course, I could have more than two pieces in my system. I could have a problem like I have an ice chest, and in the ice chest I place two 12-packs of beer, a couple of apples, and a couple of turkey sandwiches. And everything's at different temperatures. The beer's really cold, the apple's at room temperature, and maybe the turkey sandwich is at room temperature. And so I give all that information. And I say, that stuff sits in the ice chest for a couple of hours, gets to equilibrium. What will the final temperature of the system be? So there we have, what did I say, two 12-packs, so that's, or two 6-packs, I think. So that's 12 cans of beer, so each can is a CM delta T. I've got the apples, so each apple is a CM delta T, and I've got the sandwiches, CM delta T. But the process is the same. It's just I'm going to have Q for beer plus Q for sandwich plus Q for apple. So not that much more complicated. It's just instead of two pieces, there's three things, or four things, or five things, whatever. The other way it gets complicated, we'll do next lecture, which is sometimes you can change the heat energy of an object without changing its temperature. And these times are what's called phase changes. So what if I said you have a hot cup of coffee and you put some ice in your coffee? Well, this is different because ice can melt. And melting ice changes how things work. You're not just warming up the ice like you warmed up the milk. You're melting the ice and then warming it up as well. And we'll see how does that affect things. For now, this is the amount of calorimetry we're going to do. CM delta T is the main equation. You know the C's based on the problem. You know the mass, whatever. Which thing is it you're looking for? Sometimes it's final temperature. Sometimes it's the mass. And you plug everything into your equation. You have one unknown sitting there, and you solve for the unknown. So I will be posting, of course, the practice problems, so you can start taking a look at them. If you have any questions, of course, please email me. Let me know, and I'll be happy to help. I will also be creating another video with example problems, more example problems for this, so you can kind of listen to my explanation of how I go about solving some. But you're going to find, after you do a couple of these, it starts to make sense. It really is straightforward. They're all done the same way. As long as you do the algebra part at the end correct, you should be good. So, good luck. I hope this makes sense, and I will see you next time.